If we have to isolate, because we test positive, how are we supposed to get the annotation for the
So you have to
classes then?
request a note taker.
Okay. Like it wouldn't just be easier just to post the annotated slides, just in case like it happens to more than just one person.
So, I mean, before COVID, people got sick as well. I mean, it was regular that we have like at each lecture 5 to 10 students that were sick for flu or whatever reason. So note taking is a thing. So you can ask one of your classmates to take note for you and share the note with you. Any other question? No, so let's jump into the end of lecture 10, and then we'll jump to lecture 11, which is will cover all of chapter 29 of Stairway. So last time we stopped, we were discussing the force between two parallel currents, and we derived that the force per unit length, so it's force divided by a length, is equal to mu zero I1, I2, so current in wire 1, current in wire 2, divided by 2 pi r, r between the distance between the two wires. So the force is attractive for currents in the same direction and repulsive for currents in opposite direction. So here I put the link to the demo I showed you last time, so you can rewatch it at home if you want. And we're gonna use this to solve a problem. So here we have a triangular wire array. So we consider two infinitely long parallel wire that are 4 millimeters apart, and they are carrying a current of 150 amp each. A third wire that has a mass of 1 kilogram and a length of 20 meters is levitated 6 millimeters above the plane of the two parallel wire. And we want to know what the current must be in the flowing in the levitated wire for this configuration to be stable. So let's first identify the given. So two infinitely long wire, 4 millimeter apart, 150 amp each. The third wire, 1 kilogram, a length of 20 meters, 6 millimeter above as the plane of the two parallel wires. And if you look at the schematic, there is two important information as well. So you see the two infinitely long wires have a current in one direction, and the levitating wire has a current in the other direction. This comes directly from the fact that if we want to levitate the wire, we need to balance for gravity, so we need repulsive force for the levitating wire. So let's try to solve this. So the given, so we have two long wire, 4 millimeter apart. With currents that we will call here I2 equal 150 amps. And we have a third wire of mass equal 1 kilogram and length equal 20 meter and levitating 6 millimeter above the two parallel wires. And it carries a current, carrying a current I2. So when you have a situation like this, so you see here you have a 3D schematic, which is not necessarily very easy to solve the problem like that. So we can redo the schematic. So we have the two parallel wires. They are 4 millimeters apart. And they're carrying the current in the same direction. So we are going to put our I right there. So that means the current is flowing toward us. Then we have a third wire that is levitating 6 millimeters above the plane. So we know this distance here is 6 millimeters. And it's in between the two wires. So the distance here is the same, and we call this lower script L, and the current is flowing in the reverse direction because we want a repulsive force with those two wires. So now we're in a configuration where we're at equilibrium, so the wire is levitating, so there are three forces acting on this upper wire. So there is the weight, which is mg. There is the repulsive force due to wire 1. So we'll call this F1. And there is a repulsive force due to wire 2. We'll call this F2, and the resulting force is a vector force of the two. So it's something like that. So F total. So we're gonna implement a system of coordinates. So k hat, because we want the weight to be in the z direction, which means we have j hat like that, and I hat coming toward us. Here, before we try to solve this, so I already kind of did it already. So there's a symmetry in the situation. Okay, so the wire, the top wire here is in the middle plane of the two wires there. So that means when you calculate the repulsive force, because the current at the bottom here, you have I2, here you have I2, and at the top here you have I1. So the force F1 in magnitude has to be exactly the same as the force F2 in magnitude. So it's not very clean in the schematic, but therefore the component along J cancel each other, and you just have a component along K. So due to symmetry, the J hat component of the forces cancel each other. So in the stable configuration, so you have a static configuration. So you have three forces acting on the top wire. So you have mg plus f1 plus f2 must be equal to 0. Okay, so the wire doesn't move. So now the question is just to find what are f1 and f2, and we're gonna restrain ourselves to the k hat direction because we know the j hat direction has no importance right there. So we can just write on the k axis, we have minus mg plus f1, so along k, plus f2 along k equals 0, because that's the only axis that matters. Any question until now? Clear for everyone? All right, so let's pursue. So now we want to know the force. So if we're just interested in F1, so F1 along K will be mu0 I1 I2 divided by 2 pi L. So L is this distance from wire 1 to the top wire. And we have to make a projection of this force on the k-axis. So if we call this angle here theta, we obviously have the same angle here theta. So we have cosine theta, and it's not a force per unit length, it's a total force here. So we need to multiply by the length, the total length of the top wire. So here the top wire has a finite length equal to L equal 20 meters. Does that make sense for everyone? Yes? All right, so let's continue then. So we need to calculate a few quantities. So this here, this lowercase l, so the distance between wire 1 and the top wire, is equal to, so the square root of a 6 millimeter square plus 4 divided by 2 square millimeter, which gives you L equal, so lowercase l equal to 6.32 millimeter. And just for information, L squared is exactly equal to 40 square millimeter. Makes sense for everyone? All right, so now we have everything we need to continue the problem. One thing, we can still use trigonometry, so we can also define the cosine of theta. So the cosine of theta is just the adjacent side. So here we call it h, so h equal 6 millimeter. So that's this length here. So it's h divided by lowercase l. So now we have everything. So we don't need to calculate this force here because by symmetry it's exactly the same when you make the projection on the k-hat direction. Same current, same distance, so same magnitude of the force and same angles. So at equilibrium, we must have mg, which is the weight, is equal to 2 times the force we just calculated. So mu0 I1 I2 divided by 2 pi L. Cosine theta are already replaced by h over L, and I multiply by the length of my wire. So this 2 here comes because we have 2 wires that act on the levitating wire.
Wait, sorry, you said you multiplied by the L at the end because this force is only acting on the 20
Yes.
that
Yes.
it is?
So there will be a repulsive force on the 2 bottom wire, but that's not what we're interested in. And we know we're only interested in the top wire, and the top wire in the given has a length of 20 meters. So
Gotcha.
Since we know the formula for the force per unit length, here this L is given. That's the capital L here. So you just move it from the fraction here to the right side there.
Oh, it's already, okay.
Okay.
Yeah.
So you have everything to solve the problem. So you can just reverse this equation. We're interested in the current in the top wire, which is called I1. So you have I1 is equal to mg times, so you can already simplify the 2 here. So it's times pi. So L times L is L square divided by mu0 I2 H capital L. Okay, so I took this equation and then I extract I1 to answer the question. So we have everything. So we have I1 is equal to 1.0 kilogram times 9.80 meter divided by second square. times pi times 40 millimeters square. So that's why I gave it to you here, L square. Divided by mu 0, so it's 4 pi 10 to the minus 7 Tesla meter divided by amps times 6 millimeter times 20 meter times 150 amps, the H2. And if you calculate this, and I haven't made any mistake using my calculator, you should find 54.5 amps. Okay.
So next to the pi, is that a 40 meters squared?
Yes, 40 millimeters square.
Oh, right, yeah.
So I can actually put it in SI units. So it's 40 10 to the minus 6 square meter. So you have only SI units everywhere. All right.
So is there a difference with the capital L and the small l? Because
Yes.
I'm not sure.
So the capital L, that's the length of the top wire.
Okay.
The lowercase l is the distance between the bottom wire and the levitating wire. Okay. Any other question? All right, so let's wrap up the first part of chapter 29. So this force between two wires can actually be used to define amperes and coulombs, which are international units. So if you consider the force between two wires, so that's the formula we've been using. So the force per unit length is Fb divided by L equal mu 0 I1 I2 divided by 2 pi R. So if we consider wire carrying identical currents and we take a length of 1 meter, then if we have Fb over L equal 2 10 to the minus 7 Newton per meter, and mu 0, we know it's a constant 4 pi 10 to the minus 7 Tesla meter divided by amps. What is the value of the current? Well, you can just plug that in here, and what you will obtain immediately, I mean, we can directly solve that. So 2 10 to the minus 7 equal to 4 pi 10 to the minus 7. The current is identical in the two wires, so I can just put I square divided by 2 pi on R is equal to 1 meter. So 10 to the minus 7 to simplify with 10 to the minus 7, pi simplified with pi. 4 divided by 2 is equal to 2, so 2 simplifies, so we have I square equal 1, so I equal 1. So if we have those conditions, then the value of the current is exactly 1 amp. So that's what was used actually to define historically the ampere with what we call a current balance. So here we have a picture of the of one of the first current balance. And so setting the force per unit length between two 1 amps current allows you, and separated by 1 meters, define actually the value of the ampere and the value of the permeability of free space. And since the quantity of charge that flow in 1 second through the cross section of the conductor carrying 1 ampere is exactly 1 coulomb, so you have also a definition for the coulomb. Okay, so this is just like how to use physical phenomena to define a physical constant. So here is a key equation of first part of chapter 29. So permeability of free space, so 4 pi 10 to the minus 7 Tesla meter divided by amps. The Biot and Sabat law, so dB equal mu 0 divided by 4 pi I dl cross R over R squared. So here it should be a R at, not R vector. And the magnetic field due to a long straight wire is mu 0 I divided by 2 pi R. The direction is given by the right hand rule. and the force per unit length between two carrying wires, FB divided by L in absolute value mu0 I1 I2 divided by 2 pi r. So if in the same direction it's an attractive force, it's in reverse direction, it's repulsive force. So at the end of the slide, you find some complementary lecture from MIT that are covering the exact same topic. And now we're gonna jump to the second part of chapter 29.
Could you go back up quickly right before the current balance picture? One above it.
All right, so here what you see, so you have something that define a length of scale, so it's a bit blurry. I couldn't find a better quality picture for this historical device.
I think you meant the one
Yeah,
above it.
the slide above that one.
Oh, this one?
Sorry. Yeah. Oh, okay. I just didn't see the bottom part, but I guess it makes sense. It's just how you say that it equals 1. Okay. That's good. Thank you.
All right, thanks.
Sir, if you go back to the example,
Yeah.
I was wondering why you use 40 millimeters and not convert that to meters.
Oh, I converted it like 40, 10 to the
Oh,
minus
okay.
6.
Okay.
Other question? All right, let's move to the second part of chapter 29. So till now we've seen the Biot and Savart law, which relates creation of magnetic field to current. We have seen the magnetic field created by a straight wire, the magnetic force between two parallel currents. So now we are going to see the magnetic field created by a current loop. Is the Ampere's law, very important law that allows you to simplify your calculation tremendously. Then we'll discuss solenoids and toroids, and if we have time, we'll discuss magnetism in matter. So by the end of this lecture, you should be explain how the Biot and Savart law is used to determine the magnetic field due to a current in a loop of wire at a point along a line perpendicular to the plane of the loop, so along the axis of the loop basically. Explain how Ampere's law relates the magnetic field produced by current to the value of the current. Establish a relationship for how the magnetic field of a solenoid varies with the distance and current by using the Biot-Savart law and Ampere's law. And finally, establish a relationship for how the magnetic field of a toroid varies with distance and current by using Ampere's law. So for now, it sounds obscure, but you will understand by the end of this lecture. So let's jump into it. So we're first interested in the magnetic field of a current loop. So we've seen like straight wire, but what happens if you have a loop actually? So you have this loop here of metal and you have a current here going anti-clockwise into this loop. So you know, like each pieces of wire, so here ds, will create a small magnetic field dB. And if you want the total magnetic field, you of course need to consider the entire loop, and you will have to, as we did for the straight wire, to make a summation over the entire loop, or because we are going to very, very tiny part of the loop, we will end up with an integral. Okay, so that's the idea of what we want to do. So the situation is slightly more complicated than for a straight wire. So we can start by having a side view of the situation. So if I put my eye here, what I see from the side is just on the top a current coming towards me, at the bottom a current going away from me, here in the middle that will be my x-axis, and here the distance there is just the radius of the loop. We're interested at point P, right there. And
wait, sorry, how do we know that above is towards you and below is
see the current is turning like that in the loop of wire. So if your eyes is on this side and you look
Oh,
there,
that angle. Okay.
okay.
Sorry. Yeah.
So we're testing in point P here, and we want to know what is the magnetic field created by this loop of wire here. So we have to use the Biot and Savart law. So we know like it's dB equal mu0 over 4 pi I ds cross r hat over r square. So the distance r is here, and my r hat vector, unit vector, is something like that. Can you identify a symmetry in this situation?
All the y components will cancel out, and it will just be the x.
Yeah, and
Or-
what kind of symmetry? Can you put a name on this symmetry? So you're right, but just like
I don't know what it would be called.
it's a cylindrical symmetry, basically.
Oh, okay.
Okay, you turn around the x-axis and nothing changes. Okay, here arbitrarily we put the y going up and the z going to the left, but we could turn those two axes like that. Wouldn't change anything to the situation. Okay, because we can turn around this x-axis without any trouble. So we have a cylindrical symmetry. Okay. And you are right. At the end, every component that is not on the x-axis will cancel. But we will show this. So we can look at a small element. So just here, just so it's not here, it's a special case. You see, you have the ds element on this picture that is actually parallel to the z-axis and perpendicular to the y-axis. So this is not very convenient when we want to have a general picture of what happened. So for the calculation, I will take a ds that is right there. Okay, so it's neither parallel to the z-axis and perpendicular to the y-axis. Same here, I wouldn't take a vertical ds there because it would be parallel to the y-axis. So I take something in between. So we have a very, very general case. So here I have to change. So here it's called A actually, the radius is A. So if I use a cylindrical coordinate, so my ds here, the general one I choose, will just be r d theta d phi, sorry, because theta is this angle. So here, this small angle here, I will call it d phi. And we are turning in the counterclockwise direction, so I can just attach to it the unit vector phi hat. R, that connects my wire to my point P of interest, so I need to define my r hat and my r square here. So as you can see, the vector r vector is I just go along A here. So that would be, I'm going in the minus direction of the radius. And I will call this, sorry. So this vector here, I will call A vector. vector, not A hat. So connecting O to any point of my wire. So it's minus A vector plus, I will call this distance here X I hat. Makes sense for everyone? So if I want to go from this point here to point P, I go down along the radius, and then I go along the x-axis up to point P. Make sense? So I can use this to define my r hat, which is a unit vector. And that would be so minus a hat. So a hat is just a divided by a plus x I hat divided by a square plus x square to the power 1/2. So now I can inject this in my Biot and Savart law, and we'll get dB equal to mu0 I ds, so it's my r d phi, divided by 4 pi a square plus x square. So I have it once here. Times, so I have to use my r hat here. So I have a square plus x square to the power 1/2 coming here. And now I just have my phi hat cross product of minus a hat plus x I hat. So this looks complicated, I agree, but it will simplify. So to calculate this cross product, you can use a right-hand rule. So the I hat vector, the phi hat vector here, you see there's the same direction as ds. Okay, so ds and phi hat, they're in the same direction. I hat, you know, and a hat, wherever you are on the circle, you also know it's just along the radius. So you can use the right-hand rule, and if you use the right-hand rule, you will see like phi hat cross a hat will give you minus I hat, and you have phi hat cross I hat equal a hat. So how you get this is right-hand rule for the cross product. And you can use this in here to get your element of magnetic field. And you get mu0 I a over 4 pi a square plus x square to the power 3/2. So 3/2 come from this times that. D phi, and you will get a I hat plus x a hat. So now you can go back to a Cartesian coordinate. So I'm gonna draw a circle. So that's the loop that you see from in front of, like when you put it in front of you. So here you have point O. Here you have the radius A, and you can define the I hat vector. So it's a unit vector. And you can have the angle phi like that. So if we go on our system of coordinates here, so I can choose to put the y direction like that and the z direction like that. Okay, I've just rotated around my x-axis, so my y. So I put my y-axis horizontal. So it's just like equivalent to turning my head. So it's just more convenient for the calculation. So then my a hat vector, it's a unit vector. So it's just cosinus phi j hat plus sinus phi k hat. So I can use this in my dB. So I have mu 0 I a over 4 pi a squared plus x squared power 3 half d phi, and I will obtain a I hat plus x cosinus phi j hat plus x sinus phi k hat. So it seems like it still looks complicated, but trust me, we have simplified a lot the situation. So now if I want the total field is the integral over the loop. Okay, so I have b equal over loop of dB, which is the integral from 0 to 2 pi, because the angle phi can vary from 0 to 2 pi. So you all go around the loop of dB. And here, that's where I can simplify everything. Okay, as if you should remember from your math lecture. So if you do the integral from 0 to 2 pi of cosinus phi d phi, what is the result?
Sine.
I mean, the finite result. See, you have finite integral limits here. So if I plot cosinus phi,
0.
exactly, this will be 0. So cosinus phi will be something like that, from 0 to 2 pi. So this area here is equal to this area here. So the result is 0. And same thing, from 0 to 2 pi of sinus phi d phi, this is 0. So now if you look at dB, and if you make an integral over phi, because that's the only thing that change, this part doesn't matter, this part doesn't matter. Okay, so you immediately know, without trying to do any kind of calculation, that cos phi and sin phi, it will cancel. And the integral is already done. Okay, so this is a constant that does not depend on phi. So you have just d phi from 0 to 2 pi, the result is immediately 2 pi. So your b total will just be mu 0 I a squared over 2 a squared plus x squared to the power 3 half along I hat. And there's a special case, which is b of x equals 0 is equal to mu 0 I over 2a of along I hat. Does that make sense for everyone? So I know the math here looks complicated, Okay, and the thing here you have to remember is we're just playing with trigonometry, cosine, sine. Okay, so if you're at ease with trigonometry and playing with triangle, it's not that complicated, because the integral at the end we would obtain with cosine and sine, actually, because we're just integrating over like a circle. Those integral, you don't need to bother. You know they will be equal to 0. And the only thing you have to integral here is d phi. And there's nothing that depends on phi in the rest of the integral. Those are just constant. So the result is like immediate. It's just 2 pi. And 2 pi is simplifying with 4 pi. You just have 1/2 leaving. Make sense for everyone?
If we have this question on a question 7 or a module test, do we have to show all of that work?
No. So this is this here in the lecture. I just really want you to understand where it's coming from. Okay. So here the important results is the j hat component and the k hat component. As you could have guessed from the symmetry of the problems, they do not exist. But if you just play with trigonometry, you see like they disappear naturally. Okay. The symmetry also appears in the math and makes the calculation very simple. So what you have to remember for question 7 of an assignment of a test are those two formulas. Okay, well, you don't have to remember, you have to be able to identify them in the formula sheet and use them if needed and explain. Okay, I'm on the axis of a wire loop, therefore the formula for the magnetic field is that. I'm as a center of a wire loop, therefore the formula for the magnetic field is that. Okay. But you can have a question is, why is there no j hat and k hat component to the magnetic field? And in that case, what should be your answer?
Would it be the cos thing and sine thing are 0?
Actually, that is actually correct, but you are complicating yourself. You can just
Be
say
the symmetry, right?
exactly. That's the symmetry of the problem. Okay, because of symmetry, the only component that matter is a hi hat component. Okay, so what we can require you in assignment or in test is to identify a symmetry. Making those detailed calculation, I mean, you're first year student, you are learning the math at the same time as you're learning the physics. I'm not here to test you on the math. So maybe your math teacher can ask you to solve something that will resemble that. I'm not here to test you on the math, okay? I just want you to understand the concept. All right?
On our formula sheet, it has B equals mu naught Ni.
Yes,
then
I will explain you where it's coming
okay.
from.
Yeah.
All right, so here what we've been doing, so that's the formula here. Sorry, this should be I hat, not K hat. What we've been dealing here is we have one turn of current, okay? And I will show you in the demos. So first demo, there will be just one turn of wire.
Let's first put some iron file on.
So you can see here, that's the loop. It's not a round loop, but the principle is the same.
All right. And now a few hundred amperes through it. Tap it. And you can see close to the wires that goes in, here and here, you see circles because of the 1/r relationship. They dominate the magnetic field. But look in between here, there's a little bit of imagination. You can see these field lines going like this, just like I have there on the blackboard.
Okay, so what you've just seen here is for one turn of wire. So close to the wire, it's what we've been doing last lecture. So it's just like 1/r, so circles. And at the center, you have the contribution of the entire loop. So it's not very clear, but your magnetic field is straight up because of the symmetry of the problem. Here you have just one turn. So that's the other demo. So here you have many turns of wire.
There's about 15 turns on this. I'll connect up the terminals. Okay. I'll probably zoom in a little closer on this one. And we'll press the Morse code, tap a key, and see what happens. Here we go. Oh, wow. Okay, I'll just press it again.
All right, so as you can see, the pattern here is much cleaner than here. Any idea why?
More current or like more, I guess
So-
it'd be kind of current because there's more turn, right?
Yes, so that's the turn number that is very important. So in the first demo by Professor Lewis, there's only one turn, and the current is about 100 amps. For this demo, the current is equivalent, okay, about 100 amp as well. But the main difference is here you have 15 turns. So the loop, they add up their effect, okay? So you have 15 times the magnetic field, okay? So that's where the N is coming from in the formula sheet. So if you have N equal 1, you recover this formula. But if you have N turn, like in this demo, you had 15 terms, then your magnetic field will be 15 times that. So that is valid for one turn. But if you have N turn, so at the center of all the turn, B will be equal to mu 0 Ni over 2A I hat. Make sense for everyone? All right, so let's move then to Ampere's law. So Ampere's law is as important as Gauss's law for electricity. Okay, and it will simplify the calculation that we have to do tremendously. And I will show you this in the first case of a solenoid. So first, let's describe Ampere's law. So Ampere's law, let's consider a wire. For example, here you have this wire that carrying a current. Is it coming toward us or inside the screen here?
Yeah.
Any idea? So it's a dot, so it's coming toward us. Okay, so now you can use the right hand rule. So your thumb in the direction of the current and your hand are curling around the wire. So the magnetic field here that is created by a wire is a circle, and that goes anti-clockwise. Now we will consider a closed path, okay, that we will call an Ampere path. Okay, so two situations. So I will just separate them properly. So they're just different situation. Okay, I will call this case A, and I will call this case B. So first situation, my closed contour that has an arbitrary shape goes around the wire. Okay, so and the second case, my arbitrary contour, the yellow dotted line, does not go around the wire. And we will try to find the integral of the magnetic field along this path. Okay, so what we want to know is the integral around the closed path. So I put a circle here around my integral sign to show that it's a closed path. Okay, for this path, if I call this point A, I go from A to A. Okay, so it's a closed path of B dl, and dl is a small element of my path. Okay, I can use cylindrical coordinates. Okay, so the z-axis will just be the axis of the wire, and the plane can be decomposed along r hat, so an arbitrary radius, and the angle d theta. So my dl is just dr r hat plus r d theta theta hat. And I can calculate this integral in both cases. So what will happen? So we try to calculate this integral. So we know that our magnetic field, if you remember from last time, so we have mu 0 I over 2 pi r, and this is along theta hat. So if I do the dot product of dl with b, the r hat component is equal to 0, because r hat is perpendicular to theta hat, therefore r hat dot product theta hat equal to 0. So this integral, in both cases A or B, you can reduce it to mu 0 I divided by 2 pi r times r d theta, because the theta hat component, that's the only component that matters. So, and obviously theta hat dot theta hat is equal to 1. So you end up with mu 0 I over 2 pi. Those are constant numbers, so I can take them out of the integral of d theta. Okay, so if I go back to my case A, where I have my path capital M here, you see that I'm going around the wire. So my theta angle goes from 0 to 2 pi. Okay, so case A, I'm going around the wire, so the angle theta varies from 0 to 2 pi. So this integral d theta is 2 pi, and it ends up with the result equal to mu 0 I. Case B, with path capital N, you see that the wire is not inside my path, so my angle goes from 0 to a maximum angle, then decreasing again, goes to a minimum angle, and goes back to 0. Okay, so my integral is 0 to theta max to theta min to 0, so it's 0 to 0. So the integral of B dl must be equal to 0. So this is a very important result here. If you have your current going in the middle of your closed path, you obtain 2 pi. If you have your current, so your source of magnetic field outside of the path, then you have 0. That is the basis of Ampere's law. So Ampere's law will tell you, like, the integral of the magnetic field over a closed path is equal to mu 0 times the enclosed current. Okay, so in this example, we had one wire, I. But if you make many wire, like, then with I, so for example, 3 wires that have the same current I, you will obtain mu 0 times 3 times I. Okay, so you can see already the similarity with Gauss's law. So for Gauss's law, it was over a closed surface of E dA equal Q in over epsilon 0. So you had something inside, the source inside the surface, a closed surface, were related to the electric field. For the magnetic field, you have the current inside a closed contour, which is related to the magnetic field. Okay, so this is, of course, valid only for magnetostatic situation. If you have like changing electric fields, you have to add something to this equation. But for static situation, that's the only one we will consider in physics 156. That is the result. Any question on that before we try to use it? No? So I will show you how powerful it actually is by studying 2 very important configurations, solenoids and toroids. So if you're interested in electrical engineering or in engineering physics, coils or solenoids, that's stuff you will encounter all the time. Okay, so coils of wire are widely used in electronics to generate magnetic field and also act as antennas. And most of electrical circuits, they somehow contain some coils. Okay, so usually we use many turns of wire in a coil to increase the magnetic field generated or the strength of the detected transmitted signal for antennas. And we have different type of coil. So we have choke coil, which are short solenoid. We have multi-turn loop antenna, or we have flat spiral coil. And there is another type of winding that is a multi-turn toroidal coil, which basically you take this coil here, you bend it over itself, and you obtain this donut shape coil, which we call a toroid. Okay, so now what we want to know is what is the magnetic field created by this kind of configuration. So as you can see, for example, if we take this one, like this comprises current loop, okay, or here you have current loop as well, and here you have current loops that are getting bigger and bigger. So the base principle is we have to start from the magnetic field created by a current loop. So we have calculated the magnetic field at the center of a current loop on the previous slides, and the magnetic field pointing away from the center is slightly more complicated. Okay, so in physics 156, you don't have the mass background yet to calculate the exact shape of the magnetic field outside of the central axis, but that's how it would like. So on the central axis, because of symmetry, it's straight. Okay, direction given by the right hand rule, and when you go away from the center, the magnetic field is slightly decreasing, and the shape of it resembles of a magnetic dipole. Okay, so that's the same thing we've seen for bar magnet. If you remember our lecture, the first lecture on magnetic field, there was an image with iron filing, and the magnetic field that was created by a bar magnet had this shape as well. So with a loop of current, you can create something that resembles a magnetic dipole. So now the idea will be to combine all of this to calculate the field at the center of a multi-turn loop. So this we have already discussed. So if you have n turns of wire, where you have to take into account the n contribution of the different wires. So you have total field, which is mu0 I over 2r. So this is a field created by one turn multiplied by n. Okay, each loop is contributing to the total magnetic field. Okay, multi-turn coil with current I, magnetic field proportional to Ni. So what happened in the case of a long solenoid? So a long solenoid, where here you have a picture. So it's an apparatus you can find at for precision measurements at the International Bureau for Weights and Measurements near Paris in France. And basically here you have like thousands and thousands and thousands of turns of wire along this tube here. And this can create like extremely precise and extremely flat magnetic field at the center of the device. And that's what we will try to discuss. So here you have many turns of wire, capital N, which are wound along on a long cylindrical form of length L. So a quantity that we will define is the number of turns per unit length, which is lowercase n, as capital N divided by capital L, L being the length of the solenoid. So now let's discuss what happens. So a solenoid is built from current loops. Okay, so you are just like winding wires around the cylinder, so you have many loops like that. I mean, much tighter than that, but that's what you have basically. So let's first discuss this qualitatively. So you have a loosely wound solenoid. So you have current that is going so in there, coming towards you here, going in there, going towards you here, going in there, going towards you here, going in there, going towards you here. And you know, because it's a wire, so you have flowing current, so you are generating magnetic field. And the magnetic field inside the solenoid will be mostly uniform because each loop of wire at the center is creating a perfectly, in this case, vertical field. And when you're getting closer to the wire, so you have something which is in 1/r, but because you have many contribution of the different turn of the loop, the total magnetic field is a vector of sum, and you end up with something which is very close to 0 outside of the solenoid and mostly constant inside of the solenoid. So here we can try to derive in two ways. Okay, so now we consider a tightly wound solenoid. So each loop is touching their neighboring loop. And we have n turns over a cylinder that has a total length which is lowercase l. So we can define the number of turns per unit length as lowercase n equal capital N divided by L. Okay, so in electronics, solenoids are simply called coils most of the time, but they are the exact same thing. So now we want to find the solenoid, the magnetic field on the axis of the solenoid for a length of the solenoid which is much larger than the radius of the solenoid. So the first thing we want to do is we take the Biot and Savart law. dB equal mu0 n I a square divided by 2a square, and here we are on the z-axis, so it won't be x but z square 3/2 dz. So that is just a piece of wire. Here I take this piece of width dz, and so this piece at point P will create something that has this form, that will follow this formula here. In this width dz, we don't exactly know how many turns we have, so it's just n times dz. Okay, so the capital N you add coming here because you had n turn of wire. In this situation right there, you just know that you have n turn per unit length. The unit length here is dz with a length z. So n dz is equal to number of turn in the length dz. And my total magnetic field B will be the integral over the length of the solenoid. Of dB. And this is not an easy integral. Okay, I won't try to solve it with you because this is just pure math. It is doable. I mean, I will post on Canvas the details of this integral, but I do not expect you to know how to do it. Okay, this is crazy complicated to solve, but there is a much faster way to do it by using Ampere's law. So I can already tell you, so this was dz, z. The results for L much larger than A would be mu0 n divided by L, and this would be k hat, ni, so which you can rewrite as mu0 ni k hat. Okay, so this crazy integral that we have not tried to calculate in the limit L much larger than L, A will give you that. I will post this on Canvas. Just remember this result, and now I will demonstrate it to you just by using Ampere's law. So Ampere's law, let's remind you what is it, is the integral of B dl is equal to mu 0 times the enclosed current. So Ampere's law B dl over a closed contour is equal to mu 0 I enclosed. Here's my solenoid, okay? Very, very long solenoid. I can consider it as almost infinite, and we know we have n turn per unit length. So my closed contour, I have two choices. I can use this one here. So I will still call this contour 1. But this is actually kind of useless. Why would that be useless? Any idea? What would be the enclosed current in this path here that goes around my solenoid?
Would it be 0?
Exactly, 0, okay? You have the same number of wire going in than the wire going out. Okay, so the total current is 0. So on contour 1, on contour 1, so BDL equals 0. So the only thing I know is, it's not very useful. Okay, so I have 0. So the contour we want to use is actually this one. And that's how we call contour 2. And we will use symmetry. So by symmetry, this is an infinitely long solenoid. So because of symmetry, we know like the magnetic field inside the solenoid must be along the axis of the solenoid. And if you use the right-hand rule, so you have the wire coming in on your right hand, on the right side, coming out on the left side. So you go around with your hand and your thumb points towards the direction of the magnetic field. So the magnetic field is going up. So I will use Ampere's law. So I will use this contour, 1, 2, 3, 4. So I'm turning in this direction. And for this contour, now I can calculate the magnetic field. So inside, so on branch 1, so this is branch 1 of BDL plus branch 2 of BDL plus branch 3 of BDL plus branch 4 of BDL. And this will be equal to mu 0 E enclosed. Okay, so here on my closed contour, I have broken it down in the 4 sides of my rectangle. So for branch 1, I know my magnetic field is constant and along the branch. So on branch 1, BDL is just B times L, the length of my triangle. On branch 2, so inside the solenoid, DL and B are perpendicular, and outside there is no magnetic field. So on branch 2, PDL equals 0. On branch 3, we're outside, no magnetic field. BDL on branch 3 equals 0. And on branch 4, BDL. So the part we're outside, there's no magnetic field, so it's 0. And the part where we're inside, the magnetic field is perpendicular to the path, so it's 0 again. And now I just need to find the current enclosed in my total path, and I enclose is just the length times the number of turns per unit length. So if I apply my Ampere's law now, I know like I have B times L, it's equal to mu 0 times I, of course. Each of the wire here is carrying a current I. Mu 0 I L N. Lowercase l simplify with more lowercase l, so I have B equal mu 0 N I. So I recovered this result with minimal mass, okay? Almost no math there. Just considering symmetries, choosing a path that makes sense with respect to the symmetry. Most of the integral are 0. The only integral I have to calculate is trivial. It's just an integral of a line. And I obtain my B field inside my solenoid. Any question? No, so we can do the same for toroids now. So toroids, it's a solenoid, but you have like bend it on itself, so it has this torus shape, so it's donut shape, and you can create compact coil as well. And there here are different images, so loosely wound toroidal coil, tightly wound toroidal coil, and you can make schematic as is. So all your wire like that, so you can make a top view and you cut through the plane here to make the schematic. So that's what you obtain here. So you have current going in on the inside surface, going out on the outside surface. So here we have decreased artificially the number of wire for clarity, but you can just use Ampere theorem to calculate the magnetic field here on the yellow line. Okay, so you can use this yellow line as the Ampere contour. And if you use this yellow line as the Ampere contour, so Ampere theorem, BDL on the closed contour is equal to mu 0 I enc. On the closed contour, you see, like just by symmetry, you can appreciate that the magnetic field will be on the contour as well. So B and DL, they're parallel. So this is just time. So if we call this R, this is just equal to 2 pi R times B. And mu 0 enc enclosed, this is just the number of turn of wires, the total number of turn in your solenoid, mu 0 N I. So N, this is the total number of turn in the toroid. And the result is immediate, okay? You can directly extract B equal mu 0 Ni divided by 2 pi R, okay? The main difference with the solenoid is the magnetic field is not constant in the toroid, okay? It's stronger on the inner side than on the outer side, but otherwise that's the same technique. So I'm pretty sure you can appreciate that if you had to integrate Biot and Savart law on this very complicated geometry, you would have suffered. So now you can also recover the solenoid with the toroid formula. So if you take a radius of the toroid going to infinity, okay, well, the bending of the toroid, it's almost become flat. Okay, that's like on Earth. Like the Earth is round, but in Saskatchewan you see it as flat. And it's not because the Earth is not round, it's just because like the radius of curvature is so large with respect to what you can see that for you it looks like a straight line. That would be the same here if you took lowercase r going to infinity. So then you would just obtain 2 pi r just as the length, the perimeter of your toroid, and you obtain u0 n over I divided by L, and L is 2 pi r, and you just recover the same expression as for the solenoid. All right, so to finish very quickly, so magnetism in matter. So as I told you before, any current loop has a magnetic field and thus a magnetic dipole moment, and that includes atomic level current loop. So as a very simplified image of an atom, every electron travels as in an orbit and spin on an internal axis. Okay, so you can estimate the orbital magnetic moment. So if you consider that the electron is moving at a constant velocity v on a circular radius r, then the current, just the charge of the electron divided by the time it takes for the electron to go around the nucleus. So that will be EV divided by 2 pi r. Then you can calculate the magnetic moment as the same as you did for a current loop that we did like 2 lectures ago. And you just obtain the area, it's pi r square. So the mu is just I times pi r square. You can combine with the previous results and you will obtain mu equal 1/2 of the elementary charge times the velocity times the radius of the trajectory. And it's just time E times 2 divided by the mass of the electron times the angular moment of the electron. So I don't know if you've seen what is angular moment yet in your mechanics classes. It's not very important. The only thing you have to remember is electrons are orbiting around their nucleus. Therefore, they produce magnetic field, which is a non-zero. It's very small. And for most material, you have to combine the effect of every atoms of the material. So in total, the magnetic effect produced by the electron orbital motion will be either 0 when you combine all of them or very small. But this has importance for application. So then there are 3 types of material. Okay, there's what we call paramagnetic material. And those materials are they are weakly attracted by an externally applied magnetic field and form internal induced magnetic field in the direction of the magnetic field. Okay, so when you put a magnet close to this element, the magnetic moment of each dipole, they will want to align themselves with the applied external field to minimize the energy. And as a result, they will be weakly attracted to the magnet. So this is most element, copper, silver, gold, and they have a magnetic permeability slightly greater than 1. I will soon explain what it is. Induced magnetic moment is linear and weak, and this is due to the presence of unpaired electron in the material. Again, this is just for information. You'll see that in more details later on in your studies. Then you have the opposite of diamagnetic material, paramagnetic material. This is diamagnetic material, and they are repelled by magnetic field and form induced magnetic field in the direction opposite to that of the applied magnetic field. This is a quantum effect. We won't try to explain this here. And finally, you have ferromagnetism materials such as iron. Ferrum means iron in Latin, therefore ferromagnetism. And that's how you can form permanent magnets, and they are attracted to magnets. So ferromagnetic consists of tiny region of atom with aligned magnetic moment. So you form like small permanent magnets, and you know this as magnetic domain. And if you apply magnetic field to this material, you can align all those domains and you can create permanent magnets. So like for capacitor with dielectric, with magnetic material, when you have a magnetic material, to get the total magnetic field, you have to take into account the applied magnetic field. So this is the applied magnetic field. And the induced magnetic field. And you can, the induced magnetic field is proportional to the applied magnetic field through this constant key. And therefore, you can rewrite the total magnetic field as B equal 1 plus key B0. Okay, and this 1 plus key here, that's what we call the magnetic permeability, mu R, and is equivalent to kappa that you've seen for capacitor in the electricity part. So in a solenoid, if you put something in the solenoid, like a piece of copper, for example, the total magnetic field will be different from the magnetic field in a hollow solenoid by this factor 1 plus key. And you can also write mu as 1 plus key mu 0, which is also mu R mu 0. And it's related to the type of material you use. Okay, so one application of that is iron core. So if you put an iron core in a solenoid, because iron is a ferromagnetic material, actually this parameter key here is huge for iron, and it's nonlinear as well, but it's huge. So basically you end up with very, very strong magnetic field. And you've probably seen those electromagnets that are used in industry to lift very heavy objects. So they have a winding of currents around this iron core. So the current generates this magnetic field, and this magnetic field is amplified by the iron core. Therefore, the magnetic field that you have at the output of your electromagnet is much, much, much stronger. And with this kind of magnets, you can lift up cars, which are like this way, like many tons. Okay, and so you are combining two effects. So you create a magnetic field with a current, and you are amplifying this magnetic field by using a material that has specific properties that are used to amplify the magnetic field through this law here. All right, so this is the end of this lecture. So remember the force between two parallel currents. Remember the magnetic field generated by a single loop at its center. Remember that when you have n turns, you have to multiply by the number of turns. Remember the magnetic field inside a solenoid, mu 0 Ni, and remember the magnetic field inside a toroidal coil, mu 0 Ni divided by 2 pi r. Do you have any question? No, so that will be it for today, and we're back on track. So I will be connected for the 10 more minutes. So if you have questions, please ask them. I will be happy to answer them.
So in the previous slide where you used a small n, so the small n is basically the number of turns per unit length.
Yes, n is equal to capital N divided by the length you are considering. If lowercase l here is the length of your solenoid, you obtain the number of turns per unit length.
Okay.
I have a quick question regarding the module test.
Yep.
So where would be like the best option, like to have some problems to practice?
So in WebAssign, normally you have access to like conceptual question that will, if you do those exercises, you will check your understanding. And if you understand all of those questions, then you should be able to solve without any problem the module test. In the survey that you have access to, there's a bank of exercises as well that are typical for module test. So you can train yourself with those exercises as well.
Okay, perfect. Thank you.
Wait, sorry, you said those exercises are in WebAssign?
Yeah, so in WebAssign, you have a few exercises. So we have posted with Professor McWilliams some exercise you can train yourself, and you will have the solution to help you.
Yeah.
You also have access to the stairways through WebAssign. And at the end of each chapter, you have a bank of exercise. So you won't necessarily have the solution because, like, I mean, we don't have the right to post every solution on WebAssign unless you're ready to pay thousands of dollars, but I'm not sure you want to do that.
Yeah.
But you can train yourself on those exercises anyway. If you have a question because you're unsure of your solution, you can always ask me or any of the other instructor, hey, I've tried to solve exercise, I don't know, 28 of chapter 22. I'm unsure of my solution. Please, can you check it with me?
Right. Okay. Thank you.
No problem.
Sorry, do you mind if I ask a question about the last module, not necessarily what you taught today?
Sure, no worries.
Okay, you know those type of questions that are like two charges are sitting a certain distance from each other and then a third particle is set in between them. How do you know, or what would make the,
All right.
I don't know, what would
Let's
make
try.
it stable?
Okay, let's study the system together. So we put an axis like that, and we will call it the x-axis, and I will put a first charge here that we'll call Q1. I will put a second charge here that we call Q2, and I will be studying a charge 3 here that I will call Q3. So that's the situation you're interested in?
Yeah, basically.
So here I don't know the sign of my charge, but the only thing I know is, so we consider this is fixed, cannot move, and this one is fixed, cannot move too. So Q3 can move, and of course it will be either pushed away forever or it will settle in an equilibrium position. So here I have to consider the two forces. So I have the force 1 on 3, which is equal to KE Q1 Q3 divided by R13 square R13 hat. R13 hat is the vector that connects the unit vector that connects 1, 2, 3. Yeah, okay. Then I also to consider F 2, 3, same thing. KE Q2 Q3 R2 3 square R2 3 hat, and R2 3 hat will be like that. Okay? Makes sense until now?
Yeah, makes sense.
So now you're interested in equilibrium position. So equilibrium position would mean F13 plus F23 equal to 0. Okay?
Yep.
So if I put my points, my charge Q1 in 0, my charge Q2 in capital L, and I call this distance 0 to Q3 X, then I know I can rewrite this. So the force will only be on the x-axis, obviously. So I have my F13. I can rewrite it as KE Q1 Q3 divided by x squared, and the unit vector here is along, so 1, 2, 3 is along the x-axis, so that would just be I hat. You okay with that? Yes? No?
Wait, wouldn't 1, 3 be L minus? Oh wait, no,
That's-
sorry, never mind.
Yeah,
Yeah.
for the other one, yes.
Yeah, sorry.
So now I can do the same for F23. So KE, Q2, Q3. And now this distance here, this is L minus X square. And to go from 2 to 3, it's the reverse direction. So here, this is minus I hat. Okay? You agree with that?
Yeah, that still makes sense.
All right, so now we want equilibrium. So we want KE Q1 Q3 divided by X square minus KE Q2 Q3 divided by L minus X square equals 0. So I just use this equation. I know the expression of my two forces, so I just replace. Okay, and I don't need to put the I hat because they're both in this on the I hat direction. So it's I could add the I hat, but doesn't matter. Don't need to write it down. Okay. Make sense?
Yeah, I think I understand like how the equilibrium position is actually found. I'm just kind of confused when you say how is it stable. So like if you're given the charges of Q1 and Q2 and they're like, what charge would you have to give Q3 to make it stable? I don't get what that means.
Okay, so what it means is you can have two configurations. So at the end here, what you will obtain is a second order equation to solve. So something like ax squared plus bx plus c equals 0. And you find two values of x, one which is stable, one which is unstable. And your question is which one is stable, which one is unstable. So we'll just describe two physical solutions. Okay, imagine that the force change like that. Okay, so the total force, okay, this is total force. This is x, and here we have x. Okay, and this is F total, which would be F13 plus F23. If it has this shape, okay, if you move charge 3 here, actually, this is not the force, this is a potential energy. Total potential energy. And the force is related by minus dv over dx. Have you seen that in your dynamic classes or static classes?
Not too sure. Oh, maybe. I'm not 1,000% sure. It's not familiar.
Yeah, if you haven't seen it, I won't use it, and I will explain in another way. If you have seen it, I will use it. That's my question basically. So if you're unsure, just say no, and I don't use it. So I assume it's a no.
Yeah, you could use a different one.
Okay, so let's not do that then, because you won't understand if you don't have the background knowledge yet. So let's explain with the end. Okay, so imagine now that this is a positive charge, and this is also a positive charge, and here you have a negative charge. Okay, so this negative charge is attracted this way and is also attracted this way. So here you have F13 and this is F23. Okay, and at equilibrium, the attraction from this charge has to be equal to the attraction from this charge, so they cancel each other. You agree?
Yeah.
So now imagine you move this here. Okay, same situation, but you have moved your particle slightly to the right there. Well, due to Coulomb law, you know, like the attraction F23 will become larger, and but the attraction F13 will become smaller because the distance is increasing on one side and it's decreasing on the other side. Okay, so F23 becomes larger and F13 becomes smaller. So what happened to the particles then? You have an idea? If this force F23 is larger than F13, how will the particle move?
It'll go towards the right.
Okay, so it goes towards the right. Therefore, was this equilibrium stable or not?
No.
No. Okay, so it was an unstable equilibrium because if you move the particle out of its equilibrium position, the forces are such that it will just go further from the equilibrium position. Okay, so that's what we call an unstable equilibrium. There is a point at which the forces balance each other, but if you are either on one side or the other side, the particle will not go back to its equilibrium position. It will just continue moving away. Okay?
Okay.
So now if you have, so this was a negative charge, but now we put a positive charge. Okay, so now this is positive. Okay, positive. So now you know you have a repulsion. So this is F13, and this is F23. Okay, you are pushed away by this charge, and you are pushed away by this charge. Do you agree?
Yeah.
Okay, so now what happened? If I move my charge, same thing, right there. So I have moved it slightly to the right. Well, I'm closer to this charge, so my F23 become like that. And I'm further away from charge 1, so my F13 become like that. So now if I let the charge go, in what direction does it go back? Does it go basically?
I want to say it goes, because the force between F23 it became smaller, right? So it will go to the right.
So F23 is becoming larger. Okay.
Okay.
The force is proportional to the inverse of the distance square. So you see here the distance. This distance has become smaller. So F23 push to the left now. So if the distance has become smaller, F23 has become larger. But F13, the distance has become larger. So F13, its magnitude is smaller. Okay, the force, the electric force, is proportional to 1 over r squared. Okay, so if r increases, F decreases. Okay, and if r decreases, F increases. Okay.
Yeah, that makes sense.
So you're getting closer to charge 2. So the push due to charge 2 is becoming stronger, but the push due to charge 1 is becoming smaller. So the charge actually wants to go back to its equilibrium position. It wants to go back there. Okay, so now is it stable or unstable?
It's stable now.
Okay, and you understand why?
Yeah, that makes sense. Appreciate it. Thank you.
So that's the way you have to think when you have such problems. Move the charge from the equilibrium position, look how the forces are acting, does the total force wants to move the particle back to equilibrium, or will it go further and further from equilibrium? And that's how you will know the answer.
So if it was something like the charges, like the red charges over there, one was negative and one was positive, and they're like, put one, or what would the value of the orange charge be for it to be at an equilibrium? It would be like,
So basically, yeah. So what you would have to do in an exercise, what should be the sign of the charge? You have to figure out if it's positive and I move slightly my charge from equilibrium, in what direction are the forces? Okay, and which one are increasing, which one is decreasing? Is the total force pushing back to equilibrium or pushing away from equilibrium? Okay, if it's pushing back to equilibrium, well, you know the charge must be positive. If it's pushing away from equilibrium, then you test with negative charge. Do the same test in your head. And if it's pushed back to equilibrium, you know the charge should be negative.
Sorry, I think I'll just like say something. I'm guessing her question is, so if we have like two charges separated by like 2 meters, and the first charge is maybe like 1 coulomb, the second one is like 2 coulomb. What's the value of the third charge that will make the third charge in equilibrium? So we're looking for the value of the third charge that will make it in equilibrium.
So the value doesn't matter. Okay, the equation for equilibrium is there. So you see, you have Q3, something times Q3 minus something times Q3 equals 0. Okay, so the value of the charge by itself do not really matter.
I think I understand like what you're talking about now. So thank you.
Okay. So I don't know who was talking before you. Do you see like Q3? I can get it out of the equation.
Yeah, if you take the second one, the second force to the other side, you can just cancel Q3.
Yeah. Okay, so the position will depend on Q1 and Q2, but the equilibrium position will not depend on the third charge. The stability will depend on the third charge. So in this case here, if I had a negative charge here in the middle, it was not a stable equilibrium, but with a positive charge, it would have been a stable equilibrium. Then after, like you have different kind of thing, like it can be negative here, positive here, negative here. The situation can get more and more complicated for sure. But in any case, you end up with this kind of equation. You will end up with basically two possible equilibrium position. They can be stable, unstable, both unstable, and this will really depend on the specific problem. But how you set up the problem is always the same thing. Okay?
In a question like that, you'd have to have both outside charges be the same charge, right? Because if it was one positive, one negative, then it would just go towards whichever one the middle one opposes.
Yeah, I mean, the equilibrium position would not be necessarily in the middle then.
Yeah.
So you can have a configuration where you imagine you have a negative charge here, very large, and you have a positive charge here, smaller. Well, you can imagine that you have a positive, you have a third charge here that will be in equilibrium right there, because it's repelled by this one. So you will have a force like that, but you also have a force like that. So you can have an equilibrium position like that. But now the equilibrium position is not in the middle. It's
right.
just on one side.
Okay. Thank you.
Any other question?
Yeah, I have a quick question about this lecture. When you're talking about the key values, are those just unitless scalar values, or do they have some sort of
they have the same, they are unitless actually. So you see, like you have, if you just take this mu0 ni, this already has the unit of a magnetic field. So this 1 plus key must be unitless. So key must be unitless as well.
Okay, yeah, that's just what I wanted to make sure on. That's what I thought, but I wasn't positive. Thank you.
Any other question? So no, so if you have other question, yes?
Sorry. Yeah, regarding the practice, this conceptual practice questions we have in WebAssign, do you know if like it could be like open, because right now the ones for module 1 are closed. So
I will reopen them. Then they should still be open.
okay.
I will reopen the practice question.
Okay, thank you so much.
It's a mistake on our side. Normally they should be open till the end of the term.
Okay, thank you so much.
No problem. All right, so if you have a further question, please drop me an email. I will be happy to answer. And
yeah, sir. Oh,
yep.
sorry. Yeah, I just have one question, not relating to the studies, but about the test. So now, like, we're going back to like on in-person classes. How's the rest of the module test going to be?
It's going to be in person too.
Okay,
so
cool.
This test is online because we're still online, but from next Monday we are back in person. So the 2 next tests, unless the university decide to go online again, they will be in person.
Okay, so regarding the formula sheets, do we need to like print it out and bring, or they are going to be given to us in the test?
It will be given to you in the test.
Well,
okay.
Do we have to bring student cards? Because I don't have one, so I need to know if I need to get one.
I mean, you need a proof of ID for sure. Okay, so
like,
if it's not your student card, bring your license or
okay,
whatever.
so just anything that I can prove it's me somehow.
Yeah. Because
okay.
we don't want someone else to write the.
Yeah.
Okay, so just prove it's you. I will have a list of students. So if I can find you on the list and I can check your name, I'm fine with it.
Okay, yeah. I can bring my driver's license then. Or I might get the card either way. Okay, thank you.
No problem. All right, so then I see you on Friday for another lecture on magnetism. And good luck with studying for model test 1, and do not hesitate to send us email if you have any question before the test. So thank you very much and see you on Friday.
Thank you.
Thank you.